Hello, in this video I will present a toolchain to train cooperative autopilots in realistic driving scenarios using the autonomous vehicle simulator MontiSim and the deep learning framework EMADL. The training process is structured as following. Since the vehicles are trained using reinforcement learning and deep learning, the network architectures need to be defined using EMADL. The shown network receives the state of the simulation as input. Depending on the chosen driving configuration, this state not only contains information about the concerned vehicle, but also consists of specific parameters of other vehicles in the simulation. The reason for that is to enable a cooperation between the different vehicles. The network then processes the state information and returns a three-dimensional action as the output. This action contains a value for the velocity and the brake of the vehicle, as well as the steering angle. The used reinforcement learning algorithms offer various training parameters for definition and fine-tuning. These parameters can be defined in a separate file using the conflang. Here in this case, for example, the ROS environment is given here, as well as 3000 training episodes and a snapshot interval of 50 episodes. After the networks and parameters are defined, the target code can be generated using this install script. The script builds the target code using the jar file of the embedded MontiArc math middleware generator. This looks as following. The training process can be started using another script. It starts the training configuration in the basic simulator and then runs the generated training code. It is possible to run the training in a graphical user interface of the basic simulator or use a command line interface. Both approaches provide various options for the training process, and in this case, the options for the command line interface are shown. An important aspect of the training process is the scenario file, which is provided by the scenario path given as an option. This scenario file defines the used map, the trained number of vehicles, and their start and end positions. Furthermore, the cooperative driving approach can be selected. In this work, a new approach using self-play was introduced. Therefore, one vehicle is trained using EMADL, while all other vehicles are simulated by the self-play agent. There exist three options on how the trained vehicle during training is updated or swapped. These are, namely, no update of the trained vehicle at all, an update of the trained vehicle after each simulation step, or a swap of the trained vehicle after each trainings episode. All three options are implemented in the simulator, but during evaluation it turned out that the swap of the trained vehicle after each episode delivered the best results and is therefore recommended. To ensure an improvement of the self-play agent during training, after a pre-defined number of episodes, a snapshot of the EMADL agent is taken. When this snapshot is taken, the current policy of the EMADL agent is evaluated, and then with a new developed script, this policy is provided to the self-play agent, which then is restarted with the updated network rights. Therefore, also the self-play agent improves during training. After the training is finished, the results can be executed in the simulator using a script. The script starts the simulation with the trained agent. Then the user can select the training options. In this case, the self-play approach was used, and then a scenario is selected for execution.